So here is your potential energy diagram, also called an enthalpy diagram. Now we can clearly see that reactants have a lower energy than the products. So from this graph, we know that the reaction absorbed energy. It had to absorb energy for the products to be at a higher energy level. So what do we call a reaction that absorbs energy? Endothermic. So this graph is going to be endothermic. So we have a couple of questions that we have to answer based off of this graph. Question 1, the heat content of the reactants of the forward reaction is about how many kilojoules? Okay, the heat content of the reactants, we just look at the reactants, and it's very, very simple. It's going to be about 80 kilojoules. Then we look at the graph, number 2, the heat content of the products of the forward reaction. So here are your products. What number is that? That is going to be 160 kilojoules. Pretty simple. We're just reading the graph. The reactants 80 kilojoules, products 160 kilojoules. Number 3, the heat content of the activated complex of the forward reaction. So do you remember what the activated complex is? Okay, it's the highest point in the graph. That's when you have, if you remember the definition, every single atom involved just jumbles together to make one glob of a molecule, and that glob exists for a fraction of a second, and then it all falls apart, and then they recombine to make the products. But the activated complex is the highest point of the graph. 240 kilojoules. 240 kilojoules. The activation energy of the forward reaction. So this is the part where we're going to do a little bit of math. Okay, activation energy is just the difference from the energy of the products to the energy of that activated complex. This is your activation energy. Activation energy. So we need to do 240 minus 80. 240 minus 80 kilojoules. That's how much energy the reaction needed to absorb in order to proceed. So we do that simple math. 240 minus 80, and we come up with 160 kilojoules. 160. The heat of reaction, delta H of the forward reaction. The heat of reaction, we have to remember these definitions. The heat of reaction is just the difference between the energy of the reactants and the energy of the products. Heat of reaction. So we have 80, 160. Okay? The difference between 80 and 160. A little bit of mental math. Very, very simple. 80 kilojoules. And then of course the forward reaction, I told you earlier, endothermic. Endothermic. So the rest of the questions, they're asking for the same exact information, but it's asking about the reverse reaction. the reverse reaction, okay? So for the reverse reaction, these are going to be your reactants, and this line, that's going to be your products. Let's just say it's happening exactly as it sounds. Reverse. So in the reverse reaction, the products are at a lower energy than the reactants, which implies that the reaction gave off energy. It lost energy. So that's going to come off as exothermic. Okay? So just do everything I did, okay, for numbers 1 through 6, but do it for the reverse reaction. I'm going to leave that to you for practice. So let's go on to the next part. So write the following notation in delta H notation. The following reaction, in delta H notation. Delta H notation is rewriting this reaction, but taking that 200 kilojoules out of the equation and writing it off to the side. The challenge is it positive or negative? Is it positive or negative? Okay? Remember, these reactions, these are not mathematical sentences. A plus B. That plus sign doesn't mean addition. Okay? It just means it combined with it. It reacted with it. It doesn't mean addition. So you see plus 200 kilojoules, that doesn't mean the 200 kilojoules itself is positive. Okay? We have to think. Is this exothermic or endothermic? Well, the energy is on the reactant side. If the energy is on the reactant side, that means the reaction requires that amount of energy to proceed. It requires it. It must absorb it. If it must absorb that energy, it is endothermic. So rewriting this, A plus B yields C, delta H, 200 kilojoules. Now, it's going to be positive, okay? You can put a little plus sign there because it's absorbing it. It's absorbing it. So from the reaction's point of view, it's gaining that much energy. Endothermic reactions will absorb energy. So number 14, the enthalpy is off to the side. We have to rewrite it in standard notation. That means the heat term is in the equation. Okay, so let's rewrite this in standard notation. So we have H2 plus I2. Now, is this going to go, is this negative 250 kilojoules? Is that going to go on the reactant side or the product side? It's negative. What does that mean? Look at it from the reaction's point of view. If it's negative, does that mean the reaction gained that amount of energy or lost that amount of energy? Lost it. Okay, it lost it. That's why it's negative. It's coming from the reaction's point of view. So if it lost it, it's giving it off. It's a product. 2HI. Now, here is what I mean when I say that these plus signs aren't mathematical. You are not. This is a common mistake I've seen kids do. It says negative 250, and you are correct in putting it on the product side, but do not write negative 250 kilojoules. That is wrong. That is wrong. Remember, this doesn't mean that the number itself is negative. It doesn't mean the number is less than 0. That minus sign just means that's how much energy was given off. That's how much energy was lost. That minus sign is just code for lost energy. So we still have to put a little plus sign there. So that's what it would look like in standard notation. Okay, so I'm going to leave 15 and 16 for you to practice. 15, your energy is positive. Okay? You ought to know what that means. Number 16, the heat term is in the product side. So you have to rewrite it with the heat term off to the side, okay, like this. But is it going to be positive or negative? So I'll leave 15 and 16 for you to practice. So number 17, you actually have to draw your own potential energy diagram. And it gives you the potential energy of the reactants, the potential energy of the activated complex, and the potential energy of the products. Alrighty, so let me center this here. All right, so let's start drawing our axis. Okay, and then we have our potential energy on this side of our axis over here. So I'm going to go ahead and label that. Potential energy in kilojoules. And then this axis, that's my reaction. Okay, that's the direction my reaction will go in. So look at the information we have. Potential energy of the reactants. That's where we start. It doesn't have to be to scale as long as you've labeled these 3 points correctly. So let's say that 250, that's where we're starting, 250 kilojoules. So 250 kilojoules, I'll say that's about right here. And honestly, I'm picking this spot because I have room to write the number 250, if we're being honest, okay? So 250, that's my product. That's where I start. Potential energy of the activated complex. Remember, that is the highest point of your curve. Highest point of your curve. So I'm going to go way up here, and I'm going to go 350. Right there. So my curve is going to go all the way up to 350. Potential energy of my products, 300. So my products on the way down, I'm going to go to 300. So there's my curve. Potential energy of reactants, potential energy of my activated complex, potential energy of my products. So that is your graph. And then you have these answers, these questions to answer about your graph. Is it endothermic or exothermic? How does the potential energy change? Does it increase or decrease as a reaction proceeds? What is the value of delta H? Remember how to find delta H. Okay, delta H is pretty simple. It's just going to be change in potential energy, okay? So the potential energy of your products minus potential energy of your reactants. Products minus reactants. If it's endothermic, you're going to have a positive delta H. You'll have a positive delta H, right? Because the products will have a higher potential energy. If it's exothermic, you're going to have a negative delta H. Again, that makes sense. Exothermic means that the reactants are going to be at a higher potential energy. So a smaller number minus a bigger number, you're going to get a negative number, exothermic. So try the rest of these questions on your own. This is good practice. Okay, and we're going to have another assignment over this in the coming days. And again, comment if you have questions. And I will see you all tomorrow.